Awesome. Thank you so much. Yeah, that's it. So oh my, is it working? Yeah, is it working? Okay. So to give you a little bit of what to expect of this talk today, we are going to be talking about the opportunities and challenges that we had, and essentially the reasons and the motivations behind building a customer data lake at the first place. Then we're going to talk about the data replication protocol and what's our data mesh approach for CDC replication. Then we're going to deep dive on our streaming architecture and how we are doing the real-time analytics with Delta tables. Then we move to multi-region compliance, and we're going to talk about data residency and GDPR at scale. And finally, to wrap up, we put everything together and to see if we actually achieve what we were set to achieve. Cool. So that's the agenda. So let's get started. So what are the opportunities and challenges? Why building a customer-facing data lake at the first place, right? So we need to have a reason behind. So the first reason that we want to build a customer data lake is that we want to build a new product. We acquired a company that's called Chartio, and we want to provide our customers a way that they could connect to their data sets, their data assets that they already have at Atlassian in a seamless way. So they don't, instead of setting up a bunch of data engineering pipelines and connecting everything together and and so then they can extract the insights. We want to provide a product where the data is already there. They just log into the product, they can start writing their own SQL, they can start creating their own insights, and the value is straight away. So that was what our first reason. The second reason was data exports. So we have a bunch of customers that are migrating from on-premise solutions to the cloud solutions. And one of the consistent feedback that we got from them is that when they move to the cloud, they don't have access to the databases anymore. So they used to have a system that goes and reads the database and puts on their own data lake. And when they move to cloud, that's not available anymore. That's because the cloud is multi-tenant, and even if it was not multi-tenant, data is spread across multiple different databases, multiple different microservices. So there's not a database that you can connect in the cloud. So we want to provide our customers a way that they can access their data again, that they could connect to their data again, so they can continue to power the integrations as they move to the cloud. And thirdly, we want to provide a more efficient and cost-effective in-product analytics experience. So today, when you open analytics experience in our products, like think about a Jira dashboard. When you see those charts are hitting the production databases. And the production databases are doing a lot of more stuff other than just powering analytics. So what we want to do is to offload that processing from the operation databases and putting something that is more efficient, like columnar databases, where we could power these experiences in a more cost efficient way. So given all these reasons, we decided, like, okay, it makes sense to build a customer-facing data lake, but the first thing that you need in order to build a customer-facing data lake is the data, right? So the first challenge is, how do you actually get data out of product? So we have to make a bunch of decisions and have a bunch of things to figure out. And the first thing that we had to figure out was how we're going to be approaching the replication itself. Are we going to do a logical replication or physical replication? So just to define what they are, logical replication is when you instrument your application and you go on all your code paths that actually changes your entities, and then you instrument that code to capture the changes and send to a replication bus. On the other hand, physical replications, you connect to your database directly, and then you read the transaction logs from that database, like MySQL bin logs, for example, and then you send that to your replication bus. So that is the difference between this. So these approaches, they have different trade-offs and strengths and dimensions that we need to consider when you are using one of them. And we look on these dimensions. This is not necessarily a fully comprehensive way to compare, but these are the dimensions that matter most for us. And the first dimension that matters a lot for us was the technology dependency, like how much this approach depends on the specific technology. So on the logical replication, it really doesn't depend on any technology, right? Because if you define a well-crafted API, it doesn't really matter that the database that you're using, doesn't matter the language that you're using, you can keep using that regardless what you have. On the other hand, the physical replication really depends on what kind of database you're using. Does the database that you're using support a way to expose the transaction logs in a way that can be read? Is that a way that you can connect? Are there things that can translate and parse that? So it really depends on the technology. The other dimension that is important for us is contract stability. How often the contract can break, depending on the approach. On the logical replication, it's very, because the contract is on the code, is on the application code, it's fairly easy to create a bunch of unit tests so you can ensure that when the application is evolving, when you are changing your application, you can ensure that your contract is stable. So it's much easier to make sure that they are going to be evolving slowly and the downstream consumers are not going to break. But on the other hand, physical replication, your database is the contract. So your table is the contract. So the way the columns that we have are the contract. So if you're adding new columns, removing columns, if you are creating new tables, removing new tables, that has the impact that has the potential to impact the downstream consumers because of the changes that you're making. So the third dimension that we look is flexibility. How easy is to change? It's how easy it is for the producers, the owners of this data, is to change as they want to evolve their approach. So again, on the logical replication, it's on their code. So if they want to change the language, if they want to change their database, they're storing the data, it really doesn't matter. As long as they are sending the same data over the APIs, that's okay. Nothing's going to break. It's super flexible. Everything's going to be happy. On the other hand, physical replication, it really depends on the technology. So if they want to change for, say, they don't want to store data on Postgres anymore, they want to store data on Dynamo because it makes more sense for a new particular use case, or they are migrating because it makes more economical sense. Now they have to look, okay, what are the Dynamo capabilities that I have now, that can be comparable to the capabilities that we have in Postgres. So it's much less flexible because now they have to remember to keep parity when they are changing the system. And the final dimension is effort. Is how much you need to invest to get access to the data straight away. So you're probably thinking that everything that I said here about logical replication, it's a lot of work. And it is a lot of work because you have to go on your code base, you have to find all the possible code paths that update your entities, and you have to capture those changes, and then you have to worry about transactions, and then you have to put that on outbox patterns. So there's a lot of things that you have to consider in order to do that on your application level. On the other hand, physical replication, you just connect to your database. If you have access to the database, you have access to the data. Data is flowing day one. Very, very easy. But for us at Atlassian, it made more sense to take the longer route and do the investment up front and do all the instrumentation so we could get the benefits of having a more flexible, more stable, and a technology independent approach. So we decided to go on the journey of doing the logical replication and instrument. And so far, it's been good because things are changing a lot on the producer side, and that's not really impacting the downstream consumers, which is us and other consumers. And it's a lot of good investment, and yeah, the dividends are good. The next thing that we need to talk about is, okay, we figure out how we want to do. We want to replicate the data. We want to replicate the data on the logical way. Now you have to think about what are the schemas? What's the shape of the data that you're going to replicate on and how you're going to manage and who's going to own the schemas, right? So the way that we came to the approach that we use here is we got this inspiration from our friends that wrote the data mesh book, and we create these concepts where the source teams, the ones that are the product teams, think about Jira and Confluence, they are the ones that own the domain schema. So they're the one that owns the Jira issue. They owns the Jira product, the Jira project. and they want that schema that they're going to be using for the replication. And then we have a bunch of tooling on a centralized repository that generated a bunch of protobufs that based on those schemas so the producers can use that to send the data over the wire. And then on the other side, we have the consumer aligned schemas, which are created and owned by the use case team. So the team might want to create an analytics experience that calculates the Jira issue cycle time, which is a concern for the use case only. Or the Confluence use case team wants to create a Confluence popular page transformation. So they are the ones responsible for that schema and that transformation using SQL. And yeah, I think that's pretty much it from here. And then, okay, now that we talk about the schemas, there is also how we are going to send these schemas over the wire. So we have this, we decided to use protobufs everywhere because protobufs are a very compact format that's very good for sending data. And this doesn't take too much bytes to represent information and have very good backwards compatibility. And yeah, that's pretty much what we're going to say about protobufs. Our friends from Safety Culture are going to talk much more about protobufs in the next talk. And in this replication envelope, we also have something that's called last right-in strategy. So instead of having to deal with, instead of forcing our consumers to use ordering and making sure that they are sending your data in order so we can converge to the late state, we only require them to send us what is the latest number, what's the latest version of the entity that you have. So that is essentially we require a monotonically increasing number here on the version. And what we do on our side, we have a last right ring approach. So the highest version is going to be what's going to be applied and available on the lake, which means that we don't have to worry about ordering because everything eventually is going to be converging to the latest version. So it makes everything much easier to deal with order because, you know, ordering is hard. And yeah, then we have the generic payload where we use the protobuf any, and this is where the schemas that you saw on the previous slide here, where it is here, they are generated, they are created a bunch of protobufs, and they go over here on the payload of the envelope. And if this payload is too big, think about a massive Confluence page or a massive Jira ticket, instead of sending all the bytes on the message itself, we write the bytes into an S3 object and then send the bytes of the S3 object as a pointer. And then instead of sending all the bytes, you just send a reference to the object. And in the other side, when you're processing, you download the object from S3. So you don't have to deal with limits that in Kinesis or Kafka for the size of the messages. And yeah, that's now Paul is gonna talk about our streaming architecture and how do we process all this stuff in real time.
Thanks, Mike. Yeah, so basically that's the protocol that we've decided to use. We've decided to go forward with the data mesh principle, but I'll just talk a little bit now about how we've actually made that happen in the code and what our architecture looks like. So this diagram is basically a high-level view of what our architecture has kind of converged through after a few different iterations. So very simplistically, you've got your data products on the left. So that's your Confluence databases, your Jira databases, variety of different databases there. We've got some in Postgres, some in MongoDB, whatever the data product wants to use. We totally recognize that. All they've got to do is just send us our protobuf entities onto the Kafka topics. So then we've got our Flink job, and it's sitting there, and it's basically just responsible for listening to those protobuf messages and then applying those data mesh principles to transform the data based in a consumer-orientated way. So we have all of our models defined within dbt, and they're all defined within SQL statements that our consumers own and they model. And we consume that dbt manifest within our Flink job, which I'll talk a little bit more about in detail later. And from that, we fan out our protobuf messages into multiple different tables. So each one of these tables is consumer aligned, and it requires a SQL transformation of our protobuf into something that makes sense for the given use case. So that's this middle layer here that you can see with the boxes in S3. All of our tables are delta tables. So these are append-only delta tables. And then the last step of this diagram, which is the DB SQL clusters and this final customer layer that gets queried by the application. This is basically implementing that last write win strategy Mike was talking about before. So in order to process out-of-order events, we want to be consistent and have that monotonically increasing int reflect what the latest version is in the customer state. So we basically have a batch process that runs SQL queries that on a cadence will do that merge into using that delta merge statement. So it's basically just looking for the primary key, looking for the highest version, and then taking that there. So I guess I'll talk a little bit more about the transform process that we take and how we actually fan that out into multiple different tables, because it's a little bit interesting and different. So basically within our models, we have our source entity defined here that basically maps to a protobuf. So every single transformation that we have is a per protobuf transformation. We don't allow like cross joins or anything like that, keeping it simple. And basically all of our models get stored in a map where it's mapping the source protobuf to the various different models, and each of these models have an accompanying SQL statement. And as the Flink job ingests that data, it will recognize, yep, this is an avocado question protobuf here, and I have 3 tables I need to write to. So I'm going to write to my raw table, which is by default a no transform table that is hard-coded in for every single protobuf. And I'll explain why when we do data migration in the next couple of slides. And then it's also got these other couple of tables that it is going to transform the messages to and then write to. What this looks like in the code is we have our model defined in SQL here. So that's our DBT model. It's got some macros. It's got some other helper functions. DBT does a compiling of this and puts that in a friendly SQL language that Flink can consume. And then we basically just use the table API within Flink to just call like a simple SQL execution on this particular protobuf and then save it to an append-only delta table. So that's basically the transformation process and that first part of the journey where we're taking those consumer models and writing them to the table. Now I'll talk a little bit about how we do the last write win strategy. It's very challenging, to be honest, at scale in delta tables to have a merge statement like we have. So if you consider like a Jira database, customers may have hundreds of thousands of Jira issues. And when we get a new protobuf message in, we basically have to match that primary key against our tables, and their database goes from the beginning of time. And when we scale that out to our hundreds of thousands of customers, that's a very computationally expensive process. And it kind of flies in the face of what we're trying to do with like really frequent streaming updates via Flink. So for that reason, we've basically separated our pipeline into 2, like that previous diagram kind of highlighted, where we have our cutting edge, fresh data coming into this append-only table where we don't reconcile the last write win strategy there. And then we have our batch queries running on a slower cadence. And then a customer gets to kind of choose what they want. So they can have the fresher data, but they have to reconcile those versions themselves at query time. Or we do that for them if they wait and they want to run the big analytical queries that aren't so concerned with data freshness. So that's basically our streaming architecture and how we've sort of implemented that data mesh principle. How we do multi-region compliance is also an interesting bit that I think should probably cover here. But firstly, why don't we talk about why we decided to do multi-region? So we could have made the choice to only operate in one region, but these are basically the key points of why we've decided to fan that out and support all of the different regions that Atlassian supports today. So the first one is we want to give customers choice. For various regulations like GDPR or otherwise, they may have to have their data in a particular region, but also they may just want to have their data in a particular region. And if that's the case, we want to be able to serve them. It's their data. They should be able to choose where to house it. Second one is improving the query latency. So if a customer is primarily querying from the US or the EU or Australia, it doesn't really make sense to house the data somewhere else and then have a bunch of very expensive hops every time they want to query the data. So by having the data closer to the source, they get a better user experience. They're able to query data in a more efficient manner. Third one is a major plus for us. So like I said before, that last right win strategy is very computationally expensive because it's doing very large joins with a very large table on the end. And if we get to shard our table out into 12 different regions, then the table gets a little bit smaller each time. And the incoming data that we're processing also doesn't get as big for each individual query or each individual sharding of our compute. So it basically just makes everything run a little bit smoother and a little bit easier when you have smaller tables to work with. Last one, blast radius reduction. So pretty obvious there. We don't plan to have outages, but if we do have an outage, then better to affect 1/12 of our customers than all of them. So pretty self-explanatory. So yeah, we've decided to do multi-region for those reasons. But yeah, how do we actually do it? I must say, implementing everything like we have in Terraform and Kubernetes for all of our deployment and all of our infrastructure makes things a lot easier here. We basically just rely on that to create a self-contained module. And then if we need to launch up a new region, we do have to do some work in terms of setting up networking and various other AWS regions and things like that. But all of the infrastructure gets deployed as one solid entity and solid piece. So every time we need to deploy a new region, we just take that stack that's deployed via either Terraform or Kubernetes and just, do it again. The main concern that we have around our multi-region is around how we move data around. So this is the biggest complexity, and it could happen for a number of different reasons. So a customer can choose to have their data housed in a specific region at Atlassian, and they can also choose to change it whenever they want. So if their data is housed in the US today and they just feel like moving it to the EU tomorrow, then they have the power to do that. And if they do that for Jira, then we have to move their Jira data to a new region to comply with what they've asked for. Second one is if they haven't specified where their data is going to be housed, we look at their usage patterns and we think, okay, well, they're constantly querying from the US, so maybe their data is better suited to go over there. And the last one is if, sadly, they decide to leave Atlassian and they don't want to use our product anymore, we'll have to go and delete their data. Or, they've got the right to be forgotten, so... What that actually looks like from an architecture point of view is basically encapsulated in this diagram here. So we get a request up here from our migration request handler, and it'll basically say this particular site wants to move from the US to the EU, for example, and that will trigger our copy job, which is the migration job here. And like I said before, every single time we process a message from our stream, we save those protobuf messages to that raw table, and that doesn't get any transformations done to it. It's purely there as an audit log. But being there, we can use that for our migrations. So our migration job will basically just read all of the data that we've ever consumed for that particular workspace, consume it, and then perform the exact same transformations that it would otherwise have done as part of the real-time streaming pipeline, using the exact same code, the exact same models, and it will just write them into this brand new region like it was part of the regular real-time streaming updates. This then gets consumed and merged into this last right win strategy, and they have their data at the new region. After they've done the migration, we then need to go and remove their data from the old region. So that's the next part of the request. The request handler will kick off this delete job. And once again, we're using these raw tables. We use them as the audit log, but they also tell us every message that was sent and implicitly every message that needs to be deleted. So we'll read all of these messages from the raw table and we'll generate delete messages for every single message that we've just read in. And we'll just write that back to these tables, and our transformation process will automatically take care of all of the downstream semantics for that. So yeah, that's basically how migrations work and how the streaming architecture works. I'll now hand off to Mike to sum up.
Thanks, Paul. Yeah, in the beginning we said that we want to do some stuff, and now we are just about let's wrap up and see if we actually managed to do that. So we managed to build this. We managed to build Atlassian Analytics, which is an entire new product that if you are an Atlassian customer, you can go and try by yourself. So it essentially allows you to go on the product and have access to all your data that you have at Atlassian, and then write some SQL and build a bunch of analytics experience on top of it. So yes, that's the goal number one. We managed to get it. It's there. Goal number two was data exports. We also managed to build a data export solution based on the Delta sharing protocol. So that essentially allows customers to connect to our data lake directly and fetch the files directly from S3 in a secure and cost-efficient way. So they can have access to their data again when they move to the cloud, and then that is not a blocker for us to move to the cloud anymore. And finally, we managed to ship a bunch of in-product dashboards that are powering analytics experience on the product itself, moving off the load from the databases. And this is just the beginning. We are working on many, many, many others in-product experience that are going to be even bigger than these ones. And that's pretty much it. That's our talk. Thank you very much.